In this lecture, we will be looking at how to handle pairs of lines in three-dimensional real space. So let's think about the story with pairs of lines in the xy plane, in R2. We have two possibilities. We either have parallel lines or we have intersecting lines. So if two lines are not parallel in the xy plane, then they have to intersect somewhere. So think about drawing in this picture any other line that is not parallel to these two. No matter how you draw it, sooner or later it will need to intersect one of these lines. So we have two possible states of pairs of lines in the xy plane. When we go into R3, we still do have those states. You can have lines that intersect. You can have lines that are parallel, which makes sense because the xy plane is, of course, part of R3. It's this grid is part of it, depicted here. So you could have parallel lines, intersecting lines. We also have the idea of skew lines. And so we say two lines are skew if they are non-parallel and non-intersecting. And so the idea of skew lines, let's draw an example. So suppose we have this line here in the xz plane. And then let's draw a line down here, say in the xy plane. And the way this is depicted, we see that these lines are not parallel and they never intersect. So the way we've depicted this orange line is beneath the lavender line. So they're not parallel and they're not intersecting, and this is what we call skew lines. So when we have parametric equations for two different lines, we need to determine how they relate to each other. Are they parallel? Are they intersecting? Are they skew? And the quick thing to check for is to check if they're parallel. So recall parametric equation for lines. When we look at these parametric equations for L1, we know that L1 is parallel to the vector A1, B1, C1, where we're getting these values from the parametric equations here. And L2 is parallel to the vector A2, B2, C2, again reading those as the coefficients for the parameter in these parametric equations. Since L1 is parallel to V and L2 is parallel to W, L1 and L2, the lines, are parallel if and only if these vectors V and W are parallel. And that, of course, means V would be equal to, say, some constant alpha times W. So for some constant alpha. So that's the first thing we check. But that leads us into a general algorithm that we use for pairs of lines. So given parametric equations for L1 and L2, The first thing we do is check if these vectors, reading off a parallel vector for L1 from the coefficients of t, reading off a parallel vector for L2 off the coefficients of t, if those two vectors are parallel, they're scalar multiples of each other, and so that's a quick check. If we find that these two vectors are parallel, we conclude that the lines are parallel, and we're done. If they're not parallel, we go to step 2. And in this step, we think about there being two possibilities left. One is that they are intersecting. And two, if they're not intersecting, we already confirmed they're not parallel. So if they're not parallel and they're not intersecting, then they must be skew. And so we check this by looking for a point of intersection. To do that, we pick two pairs of the parametric equations. Oftentimes you'll pick, say, x and y. And you solve those two pairs of equations simultaneously. When you solve them simultaneously, what has happened is you have found an intersecting point for the projection of the lines into the coordinate plane defined by the two variables that you chose for these parametric equations. What that's saying geometrically, suppose that we did that for x and y. What you would be doing is, let's go back to our picture, is you would think of taking a light and shining a light straight down, so in the direction of the negative z axis, and you would be finding the projection of these lines into the xy plane. So that would mean when you shine this light down, you see the shadow of these two lines in the xy plane. And because these lines aren't parallel, those shadows have to intersect in the xy plane. And so you find the point of intersection of their shadows. And when you find the intersecting point of their shadows, like in this case here, if we drew this, the orange line is already in the xy plane, but the shadow of the lavender line would be in the xy plane, and we would then find this point of intersection of those shadows. Once you find that point, then you check the z values. So we have this z value for the orange line, and then for the lavender line, we would go up here, and we would find that these lines do not intersect, because if they did, they would have to intersect where at the values where the shadows in the xy plane intersected. If they don't intersect, one line passes over the other, and they are skew. And so this is the idea. So you pick two equations, any two. Usually we pick x and y. May not always work to pick x and y, but it's a good starting point. So we pick the equations for x and y. We solve them simultaneously. And we also note that you have to give, usually you're given your parametric equations like this, where the parameter is just t. But you have to give each line its own parameter. So we usually will give one of the lines s. But again, the problems are usually given to you where the parameter is the same. And the reason we do this, think back to our idea of parametric equations. We think of parametric equations for a line as t you can think of as specifying time. And as you run the clock, this equation gives you the coordinate, the x coordinate of a particle moving along the line. This equation gives you the y coordinate, and this equation gives you the z coordinate at time t. And so each one of these lines, the way they're parameterized, have their own clock. So each one has its point moving along the line in time. And because of that, you have to give each line its own parameter because you want to know, for the parametrization of this orange line, what time is it when the particle is here? And for the parametrization for the lavender line, what time is it when the particle is here? So you need to know the time where this, for each line, where the intersection of these shadows, this projection in the xy plane, occur. So this is best seen via an example. So let's determine if these two lines are parallel, intersecting, or skew. So the first thing we do is we check to see if they're parallel. And we see L1 has parallel vector. Remember, we pull the coefficients of the parameter. So we have 0, 1, 2. In L2, we have a parallel vector 2, 1, minus 4. And we can see right away that these are not scalar multiples of each other. We can't multiply v by anything to get w because it has a 0 here in the first entry. So we see, no, they are not parallel. Now let's check to see if they're intersecting. And let's concentrate on the xy equations. And we solve these simultaneously. So we have x equals 1 and y equals t plus 1. And we have x equals 2s minus 1 and y equals s. We then set these equal to each other to solve them simultaneously. That gives us 1 equals 2s minus 1 and t plus 1 equals s. Two equations and two unknowns. So we can substitute t plus 1 for s up here. So we get 1 equals 2 times the quantity, t plus 1 minus 1. Add 1 to both sides, 2 equals 2 quantity t plus 1. Divide both sides by 2. 1 equals t plus 1. Subtract 1 from both sides. We get t equals 0. Since t equals 0, we plug that in here, and we see s equals 1. So what we have just determined is that, let's go back to our picture, at time t equals 0 and time s equals 1, we have the shadows, the projections of these two lines in the xy plane intersecting. And now we just need to check if their z values match. If they do, we found an intersection point. If they don't, one line passes over the other. How do we do that? Check your z coordinates. So for L1, we're looking at t equals 0. Well, we have x equals 1, y equals 0 plus 1, or 1. And the value we really care about right now, z equals 2 times 0 minus 1, or minus 1. So we have just found the point 1, 1, minus 1 on the first line. And we know that the 1, 1 in these xy coordinates should match for L2 because that's what we solved for algebraically in this step over here. But it's the z coordinate that we're curious about. So at time 1, let's check where we are on L2. So for the x-coordinate, we have 2 times 1 minus 1, or 1. For the y-coordinate, we have 1. And for the z-coordinate, we have minus 4 times 1 plus 3. Or minus 1, and thus we see the point 1, 1, minus 1 is on L2. And we thus have found a point of intersection. This point is on both lines. So 1, 1, minus 1 is the point at which these lines intersect. If these z values had been different, we would conclude that the lines are skew. We can draw this just to get a sense of what this looks like. So first of all, we know the point 1, 1, minus 1 is on both lines. So 1, 1, minus 1. So 1 along the x-axis, 1 along the y-axis, and then down 1. So we know this point here is on both lines. And then let's just pick a point on each of the other lines. So say for L2, we are, say at time s equals 0. At time s equals 0, we would be at the point minus 1, 0, 3, just by plugging in s equals 0 here. So we get minus 1, 0, 3. So we can depict that point for L2. So we have minus 1, 0, 3. And so L2 passes through these 2 points. So we can now draw that. And to find a point for L1, we'll need to choose a time different than 0. Let's say time t equals 1. At time 1, we have 1, 1 plus 1 is 2, and then 2 times 1 is 2 minus 1, 1. So we have the point 1, 2, 1, which depicted, we come out 1 along the x-axis, 2 along the y-axis, and then up 1. So we have this point here. And again, we know that it must go through that intersecting point. And so this is our L1. And so this is the picture for these two lines. But again, this approach will always work. First, check to see if they're parallel. If they're not parallel, then they have to be either skew or intersecting. And you check that step by just trying to find an intersection point. And you either find one or you don't. And you do that by projecting the lines into one of the coordinate planes, finding where their shadows intersect, and then checking the other coordinate to see if those values match. And if you find a match, then you found an intersection point. If you don't, then the lines are skewed.